Right, well, hello everyone, and welcome to this Network Heating and Cooling webinar. I'm Dr. Andy Smallbone. I'm an associate professor at Durham, and I am the Network Plus director. And so this event is organised through the EPSRC Network Plus for the decarbonisation of heating and cooling, and part of a series looking at the different challenges of decarbonising our heating and cooling sector and behaviour. This month, we are delighted to welcome speakers from Edinburgh and Cardiff universities who have both led projects which have been funded by the Network Plus and researching into the impact of electricity market reform on the electrification of heat and the increased risk of urban overheating caused by heat pumps. We're grateful to both presenters for providing their time today. We're going to move straight over to hearing from Xiaoxiong Xie from the University of Cardiff, who will present on the project Increasing Urban Overheating Risk from Cooling Decarbonisation by Heat Pumps. And Dr. Xie is a research associate at the Welsh School of Architecture, specialising in the link between outdoor and indoor environments. He has expertise in the city and building scale modelling, and his research focuses on investigating the impact of global warming and local climate on urban occupants. And he is going to introduce this project, which explores the potential impacts of adopting air source heat pumps for cooling purposes on the local climate.
So yes, our project is about looking at another part of the heat pumps. So it's for cooling, because currently for the UK homes is heating dominant, but as we have experienced several hot summers in the recent years, so start to think about what about in the future. So maybe in the future the weather is getting hotter, and the heat pumps will be more used for cooling purposes. So in this case, what will be the influence of heat pumps for cooling on the urban climate? So will it increase the overheating risk of cities? So that's the question we are going to address in this project. So Andrew has mentioned lots of the context of heat pumps in the UK. So I'm just briefly introduced, because the UK is setting a goal to achieve net zero emissions by 2050. And it requires lots of transformative changes in different sectors, such as buildings. And for the UK buildings, for homes, the space heating is consuming the most energy, which is about 60%. They are currently most relied on the gas boilers, which consumes natural gas. To achieve the goal of net zero by 2050, there's a need to reduce the dependence on some traditional heating devices such as gas boilers. And the central strategy here is to shift the gas boilers to heat pumps. So, for example, from 1% currently to 53% in 2050. And also, as I just mentioned, the UK has the traditionally mild climate, so homes have the dominant heating needs. But with the climate change, the cooling demands of UK homes can be increased in the future. And for heat pumps, they are expected to play a dual role in both cooling and heating. And because when operated in cooling mode, the air source heat pumps, they release heat because they remove heat from indoors to outdoors. So this could be a problem, especially for some dense urban areas when there's a intense usage of heat pumps, because it may increase urban temperature. So this addressed the research question. So will adopting air source heat pumps for cooling increase the local scale outdoor air temperature, and also the indoor heating risk of some other buildings in the neighborhood that without air source heat pumps? But our objectives are assessing the impact of adopting air source heat pumps, firstly on the outdoor climate, and secondly on the indoor environment of naturally ventilated buildings. So to assess this, we are looking at the building in the urban context, and it's influenced by different factors, and such as the different radiations, the heat storage, the emissions in the urban context, and also overshadowing from surrounding buildings, and the wind sheltering effect, and also there's vegetations in the urban environment. So in this case, we need a multi-scale modeling scheme to consider of this effect on buildings. And so we combine the Swiss and H+. The Swiss is a local scale land surface model, so it can model the local scale climate, and H+ is the building scale climate model, and so it's basically a building energy simulation tool, which is used to simulate the building energy use. It can be used to assess the indoor thermal environment. So Swiss has been well evaluated in different climates globally, and it's It's based on this urban energy balance equation. So basically, the suites just need some commonly available meteorological data and some surface characteristics, like the land cover information, the albedo of the surface, something like that. And to simulate the surface energy fluxes, use the equation, and then derive the wind, temperature, and the humidity profiles in the neighborhood. And in Swiss, the anthropogenic heat emission from buildings is calculated with this equation. And so here the rho pop is the population density, and AF0 is it's a coefficient representing the non-temperature dependent QF. And AF1 is one related to the cooling degrees. So it's a coefficient representing the dependence of the QF emissions based on the cooling. And also the AF2 is one based on the heating. And these coefficients can be derived by different approaches. And so basically, they follow a shape of either U or V. So for example, in Shanghai, there's a U shape, and we can see that. So it's the relationship between the anthropogenic heat to the air temperature, and when the temperature is becoming higher, the use of energy for cooling is increased. So the heat emission is becoming larger. But for London case, because currently London has a very mild climate, so there's no cooling needs basically. So there's only heating needs which is the left part of this curve, and for the right part, it's becoming flat because as the temperature increase, the use of energy is not increased significantly. And so basically, these charts can be obtained by different approaches, such as up-down approaches, which is using the city scale energy use information, or the bottom-up approach, which is using the building energy simulation to calculate the project heat emission from buildings. Because in our case, we are going to look at the future London scenarios, so we are going to use the bottom-up approach to use the building energy simulation to obtain the QF. Also, we are going to use Energy Plus, so it's one of the most widely used building energy simulation tool, and it's well evaluated, and it's open source so that it can be combined with other models in different scales, such as Swiss. And the workflow of our multi-scale modeling scheme is that firstly we use Energy Plus to simulate the building energy used to obtain the daily relationship between the QF and the outdoor air temperature, just like the figures I just showed. And also we can derive coefficients from this relationship that can be used in Swiss to model the local scale climate that has accounted for the impact of different cooling heating systems, such as gas boilers and heat pumps. And also in another case, this local scale climate data can be used to drive Energy Plus again to simulate the indoor thermal environment of buildings that base out air source heat pumps. And so we are looking at a low-res neighborhood. So it's the residential neighborhood, which is the idealized, and it consists of identical detached houses with the planned area fraction of 0.5. So we just assume that in one case, all of the buildings in the neighborhood are installed with gas boilers, so it's the prevailing system. And in the second case, they're all changed to air source heat pumps. So we are going to look at the impact of this change on the outdoor-indoor thermal environment. And for the building archetype, we are going to look at the UK detached house. It's assumed to be insulated cavity wall because we are looking at the future case. So we are well-insulated building is the U value of 0.5 for external walls. And also because elderly people are in higher risk of overheating. So we are looking at the elderly couple occupancy. So who are at home throughout the day. And for the two systems, firstly, the gas boiler, we assume that there's a 80% efficiency. And for the heat pumps, we assume that the COP will change with outdoor air temperature, and we use the data from the CPC AM16. And for the operating modes, we assume that the these systems are only used for occupied rooms. So I think it's more realistic because people are trying to save energy at their homes. So we take this as the base case. And for the weather data, we use the UKCP 09 design summer year data. So the DSY data, basically, they are assuming the relatively warm summer, but not at the extreme. And we are looking at the London 2050s data and the two emission scenarios, the medium emissions, which is the base case, and is the representing the balanced use of energy between the renewable and non-renewable sources. And another is the high emission scenario, which refers to intense fossil fuel use. So firstly, we use NG Plus to run the simulation to obtain the relationship between the QF and the outdoor air temperatures because we are going to derive these three coefficients. So we need the relationship between the QF divided by the rho pop and also the outdoor air temperature. So in this plot, each dot is showing the daily value, the daily mean value of the QF versus the rho pop, and is corresponding to a certain mean outdoor air temperature. And we run the simulation for the whole year so that we can obtain the fitted line from this data. So basically, these lines are there's the balanced points. For example, for the gas boiler, because it only provides heating, so only during days with relatively cool temperatures, there's some increased energy use, and when the temperature increase, this line becomes flat. So the dashed line here represents the temperature that transition occurs. So it's the base temperature that is used to calculate the cooling degree days and heating degree days. And also for the heat pump, there's both cooling and heating modes. So there's two balance points, and the slopes of these lines are just the coefficients that could be used in the Swiss simulation. So after obtaining these coefficients, we run the Swiss simulation for the typical holiday in 2050s. This is the annual change of the outdoor air temperature on that day. And we can find that the maximum temperature is just 31 degrees. So it's not exactly very high value because I think in past a few years, we've experienced like 40 degrees in the UK, which is pretty hot. But this is not at that extreme. But so first here is the difference in anthropogenic heat. So it's the difference of the heat pump minus the gas boiler. Because on this hot day, only heat pumps provide cooling, and the gas boiler is not running. So it's the difference in the anthropogenic heat emission due to using the heat pumps. And we can find that the value in the peak value occurs at the midday. So it's about 6.3 watts per meter square. And also the corresponding increase in the air temperature is around 0.03 degree. And also we are looking at the ratio of delta T2 to delta QF because this value is more important because it represents some climate sensitivity at the local scale. And by normalizing the delta T2 by delta QF, we can get better consistency to compare it with some other studies. So for this sensitivity of temperature to QF, this annual change is as expected because it's related to the boundary layer depth of the urban climate. Basically, so during the daytime, we have the solar radiation on the urban surface, so the surface becomes warmer, and the air temperature close to the surface is also warmer than those in the upper atmosphere. So due to the buoyancy, the warmer air near the surface is going to move upward. So this makes the atmosphere unstable. So there will be greater vertical mixing, which makes the urban boundary layer deeper. And so basically, when there's the sensible heat available from the surface, it will be in a larger vertical extent. So the temperature increase in this case is less sensitive to the QF. But at night, when there's no solar radiation, the surface is usually cooler than the air temperature. So which makes the bottom part of the air becomes cool, and so the atmosphere in the urban environment is more stable. So in this case, the boundary layer depths will be shallow, and so we we can consider that in this case, when there's some energy released from buildings to this shallow urban boundary layer, the volume is relatively small. The total volume of the air is relatively small than the daytime. So the increase in the available energy will lead to a larger increase in the air temperature. So in this case, the air temperature is more sensitive to the QF. So which explains this diagonal change of ratio of their delta zero, delta T to delta QF. And also we compared our result to some other studies, and we can find that although our temperature increase is very low due to the increase in the anthropogenic heat, but this ratio of delta T to delta QF is similar. But the thing is that we are looking at some other cities like Hong Kong. There's the very intense use of air conditionings, and there's the compact high-rise buildings. So there's very large emission of anthropogenic heat, so which is can be up to 300 watt per square meter. But in our case, because we are just look at the low-rise neighborhood with only two people in each house, so the increase in the anthropogenic heat emission is pretty low. It's just around 6, and so that we have the relatively small increase in the temperature. But the similar sensitivity suggests that our results are reliable, and basically the small temperature increase is just mainly due to the small QF. And we further look at the impact of the adoption of heat pumps in the neighborhood on buildings without heat pumps. So just assume that all other buildings in the neighborhood have heat pumps for cooling, and that's just one building which use the natural ventilation for cooling. So the outdoor air temperature is increased due to the adoption of air source heat pumps in other buildings, and that will also influence the indoor thermal environment of this building. But the result looks like so it's showing the indoor operative temperature in these two mainly occupied rooms. So and the shaded area shows here it's that the room is occupied, and the result shows that the increase in the operative temperature is actually low. So it's up to 0.01 degree, and so this suggests that the impacts of adopting air source heat pumps for cooling in other buildings is very small for this naturally ventilated building. And also we are looking at the different scenarios of heat pump operation, because in many studies, it's assumed that the air conditioners or the air source heat pumps are operating for the whole building instead of the single room that is occupied. So this could over predict the total anthropogenic heat emission. So we compare these two cases to understand how this can influence the results. And so the blue line is our base case, and the right line is the one with heat pumps operating for the whole building. And we can find that the delta QF is almost doubled, and as well the delta T to the temperature is also almost doubled. And for the ratio, the both case basically remains the same. And for the indoor impacts, also the indoor operating temperature difference is increased to 0.02 degree, but it's still very small, and basically it's not sensible to occupants in terms of thermal sensations. And we further look at the 2050s, the emission scenarios for the high emissions, and this shows the difference in the outdoor air temperature. So we are picking the hottest day from each emission scenarios, and for the high emission scenario, the hottest day, the peak temperature is around 1 to 2 degree warmer than the medium emissions. Is not pretty large. So as a result, we got the delta QF increase just like 0.5 watt per meter squares, and some limited increase in the air temperature, and also the shape of and the magnitude of the sensitivity of T2 to QF, it remains similar. So this shows that the difference between these two scenarios are still pretty small. And in conclusion, we found that in the UK low-rise residential areas, adopting heat pumps may result in very small effects on the local cell climate and also on the indoor thermal environment of the buildings without heat pump. But the thing is that we are looking at the case with low-rise buildings, so the impact of heat pumps could be potentially larger in some areas with more intense usage. For example, the central London, they have compact high-rise urban areas, so basically the temperature increase could be potentially larger. And also in another case is that in smaller scales, for example, if we are looking at a single outdoor unit, if it's placed very close to another building, the influence on the other building could be potentially larger. So there's some future directions we can look at. So that's it for my presentation. Thank you for listening, and I'm happy to answer questions.
Great. Thank you very much.